Okay, we're going to start this with, this is GES2, and we're going to be going through the 2021 paper June. All right, let's take a look. Question number 1, explain the units for specific heat capacity. It says explain the units. I mean, like actually explain what they mean. So it already gives me the units. So they're in joules, and it's per kilogram Kelvin. Per kilogram Kelvin. But we should explain what that means a little bit. We're going to say that this is the amount of energy, in joules required to heat 1 kilogram of material 1 degree Kelvin or Celsius, because it's the same thing, really. That's it. Explain the units. I mean, I didn't explain it, I just stated them. But I did explain them. The amount of energy required in joules to heat 1 kilogram of a material 1 degree Kelvin. That will do. Let me get on to the real stuff. There's a lot of definitions in this test, so it's worth learning them. You get a bunch of points. We'll see it later on. There's quite a few more coming up. Let's take a B. An iron casting has this much mass and it has a temperature that much. Determine the temperature after losing this much heat energy. Well, if it's using heat energy, we're going to be using Q muck T. Q muck delta T, which is energy is equal to mass times by the capacity of the heat capacity of that material change multiplied by the change in temperature. So they've given us, we'll state our units, we'll state everything out here. We've got it is, what is it, 11, but it's 1100 kilojoules, so we better pop that into regular joules. So this is 1100 kilojoules, but then regular joules would make it into a million joules, 1.1 million joules. The mass is going to be 15 kg. That's good, that's fine. We can keep it. We're popping everything into standard units, keeping everything in standard units. And then the temperature, well, actually C, my bad. C is in joules. Sometimes they give it in kilojoules. You got to make sure it's in, put it back into regular joules. That's good. And then we got this delta T thing. We're going to calculate that right now. And then we're going to work out, they actually want the temperature, the final temperature after losing it. So we'll work it out at the end. I don't want to put it in now because it will make it a bit too clunky. So, all right, let's give this a go then. Let's look at the formula. So we're just going to use Q is equal to MC delta T. And we've got 1.1 million joules is equal to the mass, which is 15, times that by its capacity of 477. And then delta T, I forgot to say, I'm going to use delta T. I'll slide it on over here. Delta T, I'm going to call that X, because that's the thing I'm finding. I like to use X for the thing I'm finding. So I'll just pop it in there as multiplied by X. And then in order to find X, well, we just divide by this. So the calculation is going to be 1.1 million divided by 15 times by the 477. Let's grab my calculator. I go drag it on here. Where has it gone? Here it is. All right, and then we'll calculate it, see what happens. We're going to do 1100,000. Just be careful all those zeros, make sure it all lines up. And divide that, we can do that by the 15 times by 477. And it gives me 153.7. 153.7. 386 degrees Celsius, right? Because we started in Celsius. No, it's just change. It's just change in temperature. My bad. It could be in Kelvin or Celsius, same thing. And then we are going to drop it down from 200. So the actual calculation we need to make is going to be, let's draw a line so they get mixed up. The actual final temperature is going to be the initial temperature, which is 200, minus the temperature drop or change in temperature. So let's do on the calculator. Let's just do 200 minus answer. We get 46.26. So 46.26, let's do 5 sig fig, 1 degrees Celsius is the final temperature. And that's what they're asking for. Determine the temperature after losing this much heat energy. It's good to go. Next one. Okay. Question number 2 says define Boyle's law. Now we always have to define Boyle's law or Charles's law. Now Charles is a guy who did a lot of traveling in hot air balloons, so I can remember his formula. Because we're using, in order to calculate these guys and define Boyle's law and Charles's law, we're always using the same kind of formula. We're actually using, in my mind, I'm using V1 T1 over P1, and this is equal to V2 T2 over P2. Now this is a combination of Boyle's law and Charles's law, and in each one you keep something constant. So you you knock out one of these variables because you keep the pressure constant, for example. Now Boyle's is all about pressure and squashing things. So he says that if you have a compressed gas, if you have a gas in a tank like this and you compress it, so let's make a gas in there. We'll say these particles of gas. And then if we compress the gas, what's going to happen is the pressure will increase. I mean, that kind of makes sense. You squash something, the pressure is going to increase, you know. So also the temperature is kept constant in that case. So I think that's enough to just say it like that. We're just going to say it that way. We're going to say a gas, we'll say the pressure of a gas will increase if the volume is decreased, and vice versa. If the temperature, or we'll just say given that the temperature is held constant. All right, that's it. That's Boyle's law. He keeps his you squash it and the pressure increases, obviously, or you stretch it and the pressure will decrease. Pretty obvious. Let's have a look then at part B. So we're using a perfect gas of initial pressure and a temperature, blah blah blah, and then it's cooled at a constant pressure. So this is actually gonna be the other one. It's gonna be Charles's law. So let's see, a perfect gas. So I'm going to be using this exact formula. We've got V1, T1, P1 is equal to V2, T2, and P2. And then because we're keeping we're keeping a constant pressure, the constant pressure can be knocked out actually. Oh, I just read the actual first part of the question, which is initial mass of the gas. Now we're going to need a different formula for that. So I'm going to hold off on this guy. In order to do part 1, we're going to use a pervert equation, which is going to be PV is equal to MRT. I'm using like acronyms, and I'm using like mnemonics to remember this stuff. Every equation that we use is normally, you can turn it into a word or something to help you remember it. So this one to me just looks like the word pervert. So I'm using PV MRT. It makes it easy to remember and to keep it all together. So I can list out all of my components here for the initial part. So the pressure is at 2.75 bar. We can't use it in bar. We have to convert it into pascals, and we have to times it by 100,000 to do that. So this is going to be 275,000 pascals. That's great. The volume, we have the volume given to us as 90 liters. 90 liters, there's 1,000 liters in a meter cubed, so we can divide that just in case. Here's 90 divided by 1,000. And we've got 0.09 meters cubed. We're not in standard units, so meters and newtons and pascals, I guess. Okay, and then the next one is the mass. That's what we're trying to calculate, initial mass of the gas. So I'm going to call my mass X. So I know I've looked at it, haven't forgotten about it. R is given as the constant, the gas constant on this one, which is given in kilojoules. I need it in joules. So it's going to be 290 joules per kilogram per Kelvin, and the temperature is the temperature that the thing is at in Kelvin as well. So the initial temperature is at 185. Then what happens is it gets cooled down. That's for the second part of the question, which I'm going to be using up here. I'm going to be using this equation. So the actual initial temperature is 185 degrees C. If I add 273 onto that, we can make it into Kelvin. So let's do 273 plus that 185. 458. Okay, 458 degrees Kelvin. That's great. Anything else? I don't think so. Once we got it lined up like that, we just need to plug and play. Just need a bit more space to do that. So let's zoom out a bit. That looks good. All right, so let's put them all in. We're going to have pressure is going to be 275,000 times by the 0.09, and that should be equal to the M, which is what we're trying to calculate, multiplied by the 290, multiplied by the 458. All right, and then in order to get the X, I'm going to transpose, which means dividing by this guy. So I'm going to copy and paste this so you can see it. It should look like that. That's my X right there. So I get my calculator and just crunch them all through. So we're going to do 275,000. Just check those numbers. All right, that makes sense. Times it by 0.09. That's good. And then we're going to divide it in brackets by the 290 times by 458. Okay, that gave me 1863. It's 0.1863 kilograms. We'll do it to 5 sig figs. I'll add another number on there. All right, so this is my initial mass of the gas. That's great. Then we're going to calculate final volume. So I'm going to do part 2 over here, and I'm going to scoot the page across so we can see it. We've got 2.75 bar. I don't need pressure. It's kept at a constant pressure. This is what I'm saying. I'm using this formula, and I just got to make sure I write down all of my variables. Let's make sure I can get this all on there. We're going to have the volume 1 is equal to that original volume. Well, it's in liters. I want it in meters, so I put it at 0.09 meters. My temperature 1 was at 185. It doesn't matter if I use, it was 185? Yeah. It doesn't matter if I use degrees Celsius or degrees Kelvin, because they're going to be cancelled out anyway. Now my V2 is what I'm trying to calculate, and then my T2 is going to be 15 degrees. So I'm going to scoot this across so I can see a bit better. We can get to work on it like this. So we've got V2 is what I'm trying to calculate, and then my T2, that was the 15. And we're ready to go. We just plug it into this one. It's a really quick one. It's going to be, let's just make it a bit more space. It's going to be 0.09 times by the temperature of 185 is equal to X times by 15. And of course we can transpose that to get 0.09 times by the 185 over 15. Let's get my calculator, try it out. 0.09 times by 185 divided by 15. 1.11. Looks like a typo, it doesn't look right. 0.09, I did it really quickly, times 185 divided by 15. 1.11. Looks like I got something wrong here. What's going on? My formula's wrong. Oh my goodness, look at that. None of these numbers are looking right. This formula is wrong right from the outset. How can I do that? It's got to be... the reason why I say that is because the numbers have to get smaller. When you decrease the temperature, so it's going down to 15, from 185 down to 15, it should get smaller instead of getting bigger. And when I look at my numbers, I do my calculation, my volume now becomes 1.1 meters, and it was 0.9, so it got bigger, but it's getting colder, so it should get smaller. So I got something really messed up. I mean, we all make mistakes, so the important thing is to pick it out. So this is wrong. This should be the temperature on the bottom and the pressure on the top. So this would be pressure on the top and temperature on the bottom. Well, luckily I fixed that. Yeah, all right. The pressure of the gas will, well, yeah, okay, it does say that, yeah, because the mass is held constant. Let's fix this guy over here. We should have the temperature on the bottom and the pressure on the top. That's pressure 1. And then we're going to have it, yeah, the pressure on the top and the temperature on the bottom. All right. Wow. Can't believe I messed that up, but we all make mistakes, so luckily I fixed it, so it's all good. So the pressure is kept constant, so we can ignore it. Now this changes my setup a little bit. So let's fix this. Let's delete all that and put it back how it should be. So the calculation should be 0.09 over 185 is equal to X. I don't know what that is, times 15. And we're going to multiply the 15 to the other side to calculate it. So just so you can see that, it's going to be 15 times by 0.09 over 185. And we're looking that the volume gets a lot smaller because it's getting colder. So here's my calculator. Let's try it. 15 times by 0.09 here equals, divide that by 185. 0.01, that's much better. So now it's 0.0, x is equal to 0.0, 1588, 235 meters cubed. Is much, much smaller. It's gone from 9 liters down to 1.5 liters, which is pretty good. I mean, it's dropped like 150 degrees, 160 degrees, 170 degrees. So it's pretty good. Okay, well, on to the next one. Okay, we're going to do question number 3, and this might be a bit of a long one because we're burning benzene in air. We're burning some benzene is completely burned in 20% excess of air, and we've got to calculate the following: carbon dioxide in the exhaust gases and the mass of nitrogen in the exhaust gases. Now this is a little bit of a weird one because, well, first of all, we're burning benzene. Second of all, we're calculating mass of carbon dioxide. We don't usually do that. We usually go straight for calculating the oxygen required. So I'm actually going to take that kind of usual route and then adapt it at the end. They always seem to adjust these a little bit for GES2. They're a little bit different here and there, different topics. We're going to need a bit more space, so I'll zoom out a bit. See if we can fit that in there. So benzene is completely burned to excess of air. I'm going to fit this in because it's going to be quite big. Benzene, and we're going to be burning 1 kilogram of fuel. So first of all, I think we've got to work out how much carbon there is in the fuel. So let's calculate the amount of carbon and hydrogen in 1 kg of fuel. I like to give my work these subtitles as I'm working through them because it makes it easier to follow, I think. So we'll give it a go like this. So the amount of carbon and hydrogen in 1 kilogram of fuel. So we've got 1 kg. The first thing we've got to do is look at how much of that is carbon and how much of that is hydrogen. They don't give us any of these formulas or any of the bits that we need. Oh, I forgot to write these down. So we need to know a couple of things, like the relative atomic mass. That's like the weight of the carbon atom of carbon is equal to 12. Oxygen is equal to 16. Hydrogen is equal to 1. We're going to need those in order to do the calculations. We also need to know that air is 23% oxygen. And then we're going to need it for the nitrogen part of it. We're going to need that 77% nitrogen. Near as nitrogen. All right, now we can get to work about calculating the amount of carbon and hydrogen in 1 kg of fuel. So let's give that a go. So we got to know how much does a molecule weigh, because what we're going to do is take the proportion of carbon in that. So let's have a look. We've actually got a carbon is equal to 12, and then if we had 6 carbons, because we've got 6 carbons in the benzene, we've got 6 carbon. That's equal to 6 times by 12, which is equal to 72, I think. Let's give it a go. 6 times by 12 is 72. This is the weight of the carbon. The hydrogen is equal to 1, and we've got 6 hydrogens. So that's going to be 6 times by 1. So the weight of all that hydrogen is 6. Now the total of this is the benzene. I don't need to work that out. I can just write down the total. It's going to be 72 plus 6, so it's 78. This is the relative molecular mass. So we can use that to work out what proportion of this is going to be carbon, what proportion is going to be hydrogen. Let's have a look. The amount of carbon then is going to be, just the carbon part is going to be that 72 out of the total amount. And then we're going to times it by 1 kilogram because we're using 1 kilogram. So it'd be 72, I was already my calculator, 72 divided by 78. And then times it by 1, the 1 doesn't do anything. But we can keep it as 12 over 13, but I'm going to write it as a decimal. It's easier to see. 0.923076. I think that's right. Yeah, okay. It repeats after that. So actually this would be a 7. That's what the brackets mean on my calculator. It means this thing repeats. I can flip it a bit more so you can see it as a fully expanded version. There we go. I'm going to round it up to 6 significant figures. All right, cool. So this is actually how many kilograms of carbon we're burning, which is really good. let's do the exact same thing for hydrogen. I'm going to leave a little space. So let's do hydrogen. Hydrogen is going to be, that's the 6 out of 78, again, times by 1. Let's write it. I can squeeze it in here. So let's do that on a calculator. We're going to 6 divided by the 78, and then we times it by 1. We got 1/13, which is equal to 76923. 0.0766923. Again, it repeats, but it repeats over 0. kg of hydrogen. That's exactly how much hydrogen we have in the fuel. That's really good. All right, let's make a bit more space so we can see everything at once. There it is. We are gonna now work out the amount of oxygen required to burn that carbon and the oxygen required to burn that hydrogen. Now, it's not the only way to do this because we want to go straight for the CO2, but I'm taking this long way around because normally the questions are like this. I don't want to change my method too much. I want to keep it basically a standard method that I can tweak and adapt a little bit rather than doing a whole different route through the calculation. So let's burn the carbon. Now, how does carbon burn? You get some carbon, you add some oxygen, and you make CO2 if it's completely burnt. And it is completely burnt. It said it's completely burnt in the question. So we need to balance this equation. So we need to have 2 oxygen molecules. So it has to be 2 oxygen atoms. It has to be C plus O2 is equal to CO2. That makes sense. It's quite common stuff. We're used to that. Now, the formula we're using is the mass divided by relative atomic mass, which are those numbers we wrote down earlier. So we got the mass of these things. What is the mass of the carbon? We are burning the mass of the carbon. That is going to be this 0.9. We got it earlier. I think we can just drag it up there. This is the mass of the carbon. Let's scoot that down a bit. We're going to be dividing that by the relative atomic mass of carbon. It's just 1 carbon atom, so we can divide it by 12. Now this must be equal to the amount of oxygen required, but we're dividing it by the molecule of O2, or because there's 2 oxygens, so it'll be 16 times by 2, so that's 32. Now this is a little calculation here that tells us how much oxygen we need. It's really easy. We just flip the 32 to the other side. So I'm not even going to write that down. I'll just calculate it straight up. We're going to be doing 0.923077 divided by 12, and then I'm just going to times it by that 32. And it should give me the amount of oxygen required. So we've got 2.46. So X is equal to 2.46. 15388. No, 1538. And a bunch of 6s. We'll call it a 7 probably. All right. So this is how much, we're going to say kg of oxygen. And that's how much oxygen we need to burn all the carbon in 1 kilogram. That's great. So that was the amount of carbon required. Now we're going to burn the hydrogen. Again, we don't really need to do this straight away, but we're going to need it for part B anyway, so we might as well write it out like this. And this is a standard setup. So let's burn that hydrogen. How do you burn hydrogen? You get some hydrogen, you add some oxygen, and it makes H2O. We do need 2 hydrogens to make that happen, because we need to have H2O, not HO. So we're going to use the same formula we have up here. We're going to say the mass divided by RAM, the relative atomic mass, and they should be balanced out. So we got the amount of hydrogen. That's this guy down here. We did it earlier. This is the amount of hydrogen we are burning. Right, and we're going to divide that by the relative atomic mass of 2 hydrogens, and 2 hydrogens is going to be 2 because 1 is 1. So 2. And this must be equal to the amount of oxygen. I'm going to use another X. I don't care. There's X's all over the place. Yeah, I don't care. I just like using it. It keeps it nice and simple. It's only for me to see. And then we're going to divide that by the oxygen. So oxygen is 16. There we go. Again, really simple calculation. We're just going to calculate this side and multiply by 16. So let's do that. The 0.076923. Divide that by 2. And then we times it by 16. And we get 6153. X is equal to 0.6153. 6153, 84. 84. So this is the kg of oxygen required, oxygen, to burn all that hydrogen, which is really, really good. Like I said, we don't need it right now. Going back to the question, because I always read the question and I get a bit lost in all this. The mass of carbon dioxide in the exhaust gas. And the amount of CO2. So now what makes the CO2? Well, this is the CO2 right here. Let's do it in another color. This is the CO2 right here. Nothing else makes carbon dioxide. Only the carbon makes carbon dioxide. The hydrogen makes water. It makes H2O. That's the vapor in the exhaust, which you see, dripping out of exhaust tailpipes or exhaust pipes. Is the hydrogen? Is the water? The H2O there. But it's going to make a bunch of CO2, but nothing else to do it. It's going to be sucking a bunch of nitrogen from the atmosphere, but that does not make any difference to CO2. So we actually just need to calculate the mass of CO2. It doesn't matter we have an excess of air. It doesn't make any more carbon. It's only sucking in this much carbon. We're burning all the carbon. That's all getting converted into CO2. And the mass of that CO2 will be equal to the mass of this carbon plus the mass of that oxygen. And we just calculate those. That's actually like the conservation of mass, but it doesn't really matter. We just calculate the mass. We know the mass of this carbon, it's right here. I know the mass of that oxygen, it's right here. So I can say the mass of CO2, let's say CO2 mass will be equal to the mass of the carbon plus the mass of the hydrogen. Nope, oxygen, and that's equal to the mass of the CO2, of the carbon dioxide. All right, so we got the mass of the carbon is right here. I'm just going to copy it across. We've got the mass of the oxygen required just for that carbon, not for the rest of it. Multiply copy and paste that across, and then we just add them together, and we're done. So let's just type them in. It's 0.923077 plus 2.46153867, and we get 3.38. I think it was a 6 after that. 61567 kg of CO2 produced. Now I could have done it another way. We could have done another calculation to go straight for the CO2, but why not just do it this way? It's exactly the same result. All right, so we got the mass of CO2. This was the first part of the question. Let's put a box around it. All right, let's go back and read the question. We have to do the mass of nitrogen in the exhaust gases per kg of fuel. So it's another bunch of calculations. In order to do this, I would normally run it on from this section right here, because we need to calculate the total amount of oxygen required to burn that fuel, and we have done. So I think I'm going to drag it down here if I have the space. I'm going to start question B. And it was the mass of nitrogen. So let's label that up as mass of nitrogen in exhaust gas. Okay, so first of all, I need to know how much oxygen was required. So we take the oxygen required for the carbon. We take the oxygen required for the hydrogen, and we add them together. Let's grab those numbers. We got them up here. Here's the mass of oxygen for the carbon. We'll write like carbon on top of that. And then the hydrogen one is this one right here. All right. That's really good. Mass of nitrogen in exhaust gas. Yes. Okay, we add these together. We get the total amount of oxygen required. So let's add them up. Let's get the total amount of oxygen required. We've got 2.46153867 plus 0.615384. Total amount of oxygen required then is 3.07 6922 67 kg. Now this is a stoichiometric amount, like just enough amount to burn that 1 kilogram of fuel. So I can't even say that, but I just said it. This is the amount of oxygen required to burn that 1 kilogram of fuel. Now we're going to add 20% onto that, because in the question, I'm going to go grab this question. In the question, it says we're going to burn it in 20% excess of air. Oh, actually, my bad. Let's calculate how much air required. How much air is required to get that amount of oxygen? So how much air do we need to suck in order to get 3.0 7 kilograms of oxygen. So let's do the amount of air. Again, this is stoichiometric. It's just enough. We're going to add the 20% on later. So the amount of air is going to be like the air amount times by 0.23, because remember, the atmosphere is 23% oxygen, and then this will be equal to that amount. It's a very simple calculation. We always do exactly the same thing. It's a reverse percentage. So the amount of air required is going to be this divided by this. It's going to be that number I got just here divided by the 0.23. It's going to reverse the percentage and give me the amount of air required. That's 13.37792 kg of air. That is just the right amount of air I need to burn all the fuel. Now we're going to add 20%. So let's plus 20% of the air because we're going to burn it in excess. So we just take this amount, this 13.37792, and times it by 1.2. That'll be adding 20%. Times by 1.2. 16.05. 16.05. 35 kg of air required. This is air. With a 20% excess. Now we're going to go to the nitrogen, because remember the nitrogen, I said, let's move it so you can see it. The nitrogen is 70%, 77% of the air. So we just take the amount of air and we multiply it by that 0.77. Nitrogen is 77% air of air by volume. So let's take the amount of air required and we just drop it down to 77%. So times it by 0.77 and it should give us the result we're looking for. We've got this number in the calculator still. We can just run it through like this. 1236. 12.36 1 kg of nitrogen. Nitrogen. This will be the amount of nitrogen in the exhaust gas. It's sucked in, used up, kicked out, and not used. Well, the oxygen is used up. The nitrogen is not really affected. Let's just check the question. Make sure we did it all. The mass of nitrogen we did. The mass of carbon dioxide we did. It's a lot of work for 4 points. It's a long question. All right, next one. Okay, we're going to do question number 6, and this is going to be quite a tough one. It's quite a big one. It's got a lot of stuff in it. I will try and make it work. Might take a while to get through it all. So, it's a 2-stroke diesel engine is tested over a 24-hour period and uses a bunch of fuel, and the power to the engine is tested using a dynamometer, which gives the torque reading of this many kilonewton meters, at 800 revolutions per minute. Mechanical efficiency was later found to be this much. Okay, it's a bunch of information, and we're going to be using a lot of different formulas on this one. Like I said, there's quite a lot in this. Let's see where we start. We should start by, I guess, listing out our formulas, the ones we could be using. Brake power. Brake power is the actual available power on the engine, coming off the axle. How do you call it? Coming off this bit, the spinny bit. Well, axle. Okay, I can't remember the name of it. Okay, that's the brake power. It's available power. There's a couple of different ways we can get this. So let's see. We might get that from efficiency, and I think in this one we're going to be doing that actually. The efficiency, this is mechanical efficiency, is brake power, because this is the actual power. That's brake power is the actual power you get off the engine, divided by the IP, which is the indicated power, which is like the theoretical power. And I think this is the one we're going to be using. There's another one for brake power as well. Let's see what else we got. Brake power is also torque is T2 pi n. Now we got to talk a little about that as n, because I'm using a slightly different version than what you'd find in the books, which I think is a good thing, because how they do it in the books is really confusing. Otherwise, you wouldn't be here. You'd be studying the existing courses. So I'm going to be doing things a little bit differently to try and simplify it, make it a little bit easier. So this is torque times by 2 pi times by n. And this n is how many effective revolutions or how many effective strokes or cycles this engine is going to go through it per second. Cycles per second, we can say. Cycles per second. We'll have a look at that in a second. Anything else? Are we going to be using another formula in a bit, which is going to be indicated power is equal to x plan. Now this n is the same n as that one. And all these bits broken down. X is the number of cylinders. We don't have the number of cylinders, so I can't do that. P is the pressure. This P is actually the is it IMEP? IMEP. It's IMEP. It's the indicated mean pressure. And this is inside of the cylinder. And this is the area. This comes from a diagram drawing, which we don't have a diagram on this one either, so we're not going to be using this one. Is area times by the spring coefficient, and you can see there's no spring coefficient on this, divided by the length. Again, we don't have a diagram information, so we can't use them. So these two we're probably not going to use, so I can just push them off to one side. It's still there. It's still part of these kind of diagrams. It's still part of these kind of questions. Okay, it's too strict. So I think we're going to be using this one, BP, or this one to start with, because the first thing we're going to do is calculate brake power. I think we can do that. Let's try it over here. We'll start with brake power. It looks like we got everything we need for this guy. Brake power is going to be the torque times by 2 pi. So let's get torque first of all. Torque is given up here. Where is it? Torque, it is has 4.5 kilonewton meters. So let's drop it into regular newton meters. So it'll be 4,500 newton meters worth of torque. 2 pi is just 2 pi. Now this n cycles per second. That's a little bit more complicated. N is the number of cycles per second. They've given us as 800. They always give it in revolutions per minute. So it's 800 revolutions per minute. And 1 minute is 60 seconds. And was 800 revolutions. We can just divide it out. We can simplify this by dividing by 60 above and below, on the top and the bottom. That'll do it for us. It's effectively just doing 800 divided by 60. So really I'm simplifying the tops, simplifying the bottoms to get 13.33333. So this is 13.33333 revolutions every second. Now because it's a 2-stroke, that's fine. We can leave it like this because that is effectively one complete cycle. A 2-stroke. If it's a 4-stroke, it would be a double. To be 2 cycles every second. So we'd have to divide this by 2. We have to share this out between the 2 effective cycles. This time we don't. We can just leave it like this. So we're good to go. And it's just this because it's a 2-stroke. If it's a 4-stroke, we'd have to divide it by 2. We'll do that again in a later example, another example. I've got everything I need for this guy. It's really, it looks like a horrible formula, but it's not actually that bad because it's pretty simple. We can just plug stuff into it now. So I can say that my brake power is going to be, I won't drop it up there, I'll drop it down here. Brake power is going to be the T, which is 4,500, times by 2 pi, times by 13.33333, recurring. Okay, so grab my calculator. I've got this 13.333 recurring in my calculator. I'll times that by 2 pi, and then times that by 4,500. And put it as a decimal, and we're going to get a big number. This is my BP. So I've done it in actual just power is done in watts. So I've done it in regular watts. So it's 376,000 watts. I could drop into kilowatts. So you could say it's 376.991 kilowatts of power, of brake power, the raw power available. That's really good. Okay, we've done part A, which isn't that bad. Let's have a look at part B. Probably need to take this with me in order to do part B. Let's have a quick look. We're going to need some more stuff. Indicated specific fuel consumption. Right, so need a new formula for that. Okay, I'll drag it off to the side over here. What is indicated specific fuel consumption? Let's have a look at that first of all. So I need a formula for this. I don't normally have it. It's a new one. It's a new one that I haven't looked at before. This whole subject to do with motors and engines is quite a difficult one. It's quite a big one. It's got a lot of information. It's one of the biggest on GES2. So indicated specific fuel consumption. consumption, and we're just gonna call that ISFC from now on, which is wonderful acronym. ISFC, I suppose, something like that. And this is, what is that? Got it written down here somewhere. It is MF over IP. Now, MF is the amount of mass of fuel. It's a mass of fuel per second. So we can work that out as being the mass of fuel per second, because we can do it in hours as well. The indicated specific fuel consumption is basically how much fuel we're using divided by the indicated power, which is the theoretical power. So it's like how much fuel you're using per second divided by how much power you should be producing. It's not the like actual power, it's the theoretical power of the engine. So let's look at how much fuel we're using. And again, I can do it per second, or I can do it per hour. We can do it in kilowatt hours, or we can do it in kilowatt seconds. I'm going to do it in watt seconds. I'm going to do it in seconds because it's standard units, but it doesn't say the units, so I can do it any way I like as long as I state my units. It should be okay. Anyway, the amount of fuel we're using every second, well, we're using 1.8 tons of fuel in a 24-hour period. So that's 1,800 kilograms of fuel in 24 hours. Let's drop that down into just 1 hour divided by 24, 75. So 75 kg in 1 hour. Let's drop that into seconds. So we can drop it into seconds by dividing by 3,600. So it's 3,600 seconds, because that's how many seconds that are in an hour. 60 times by 60, 75 kg. Okay, and we want to simplify that down to 1 second. So again, we divide by the 3,600 to get this number, 208. 0.0208, and a whole bunch of threes. Yep, that looks good. Okay, this is kilograms per second of fuel. So we're using this much fuel. We're using 20 grams of fuel every second. Great. Okay, that's my MF. My IP. Do we actually have enough information to calculate IP? Well, if I do it the other way, where I showed you earlier, there's 2 different formulas for IP. If I use my usual IP, which is X-plan, I can't do it because I don't have my number of cylinders, but I can do it from the efficiency, the mechanical efficiency of this thing, the mechanical advantage we have. We can use this one because we have BP, we just calculated it, and we have the efficiency as given as 89%. So I'm going to use that exact formula. So let's go for the efficiency, that's the mechanical efficiency, is equal to BP, the raw power available, the actual available power, divided by the IP, which is the theoretical power. Okay, so this is given. We're given that as being, let's just scoot this across. Over here. It's given as a percentage, 89%. So we know this is 0.89. My BP, I just calculated on the previous question as being all this. I'm going to copy and paste that across. There's 376. Drop it down there. And then my IP, this is exactly what we're trying to calculate. So we can drop it down here. We can flip this around by multiplying through by the denominator, multiplying through by this IP, and dividing through by this 0.89. Effectively, we're just going to write it like IP is equal to 376.991. This is in kilowatts over 0.89. Okay, let's drop that into the calculator. 376.991 divided by 0.89. 423. 423. Drop it down here. 585.585. Just check that. Yeah. Kilowatts. This is my theoretical power. This is the amount of power that the engine should be producing if it had zero friction in it. But then they were losing that power, and we're really only getting the 376 kilowatts available. Okay, so indicated. So we're getting there because we needed the IP to plug into this formula over here. I got my IP. I got my MF, which is the amount of fuel we're using every second. We can just plug these guys in. So now we can say this is equal to the 0.0208, a whole bunch of threes, divided by the 423.585 in the kilowatts. We're good to go on that. This, we're going to look at the units afterwards. Let's try and keep it as separate for now. So 0.0208, whole bunch of 3's, divided by my previous answer, because my previous answer is 423. Probably was, yes. And it gives me 4.9183. That'll do. Times by 10 to the negative 5. Now, this guy up here was in kilograms per second. This was in kilowatts. So the seconds drops down to the bottom. So the final units of this thing becomes kilograms per second kilowatts, which is a bit weird. I admit that's a bit strange. We should probably have it in kilograms per hour. But for kilowatt hours, because this is kilowatt seconds, and kilowatt seconds is a bit strange. I don't know if that's a standard unit. I kind of think kilowatt hours is a bit more normal, but we got it in seconds. So it should be fine. It's all good. Okay. Let's look at the next bit. We're going to do part C, the brake thermal efficiency. So again, I'm going to drag this across. Let's look at brake thermal efficiency. So I need another formula for this. My brake thermal efficiency. It's effectively how much power we get out of it for how much energy we put into it. So it's the brake power over the amount of actual fuel we're consuming. So it's the mass of fuel we're consuming, which we just worked out earlier. We did it in per second, kilograms per second. And then it's multiplied by the calorific content. It's the mass times by the calorific content of the fuel. So we can work out how many kilograms we're using. So yeah, we got all this stuff. Let's just write them down. Let's just get them across. It's quite an easy calculation. It's an easy 3 points once we've done all the rest of the legwork. So our BP, the brake power, is given way back here on the start. Here it is. It's a 376 kilowatts. So let me drag that across here. There's my BP. And then the M, which is the amount of fuel we're consuming every hour, every second. We did a second ago. It's this many kilograms. It's 0.2 kilograms per second. So let's drag that across. Try not to make you too dizzy. And then the calorific content, or the calorific content is this. It is in megajoules, so it's million. So we can say 44 times by 10 to the 6 if you want to do it shorthand to get it into joules per kilogram. Or I can go ahead and write down 1, 2, 3, 1, 2, 3 if you like a lot of zeros. The problem with a lot of zeros is that it's very difficult to see if you miss one. So I'm going to leave it in standard form or standard notation because I can see it a bit clearer. Cool, now we just plug them in. Brake thermal efficiency. So that brake thermal efficiency will probably be a percentage. So I have to times it by 100 at the end and to turn it into a percentage, but we'll do that part. Shouldn't be too hard. Let's just plug these guys in. So we're going to have the 376.991 kilowatts. Kilowatts. Everything else seems to be in standard units. So I guess I should drop that back down into just regular watts. Let's get rid of that decimal place. So we just got regular watts divided by kilograms and seconds. Everything else is in kilograms and seconds and kilograms. And joules and kilograms. Yeah, so it should be. This is joules per kilogram. And let's drop all these numbers in. So 0.02083333333 times by the 44 times by 10 to the 6. All right. Now we type all it in, cross our fingers, and I hope it works. Sure it will, right? So let's give it a go. We've got that number. No, I don't. That's an old number. So 476991 divided by, I put all the stuff in brackets so it all works. 0.0208333333 and times by 10. My bad. Times by 44 times by 10 to the 6. Close brackets. And looks good. 0.41. 0.41. This is the reason why it looks good. Is we're talking about percentage. So 41%. Sounds about right. It's not too efficient. It's not too inefficient. It's just about right. It's not some crazy small number. It's not some crazy big number. So again, we times it by 100. So we can say this is equal to 41.126% efficient. Great. That's it. That's the end of question 6. On to the next one. Okay, we're going to take a look at question number 9. The navigation lights on a vessel are fed by a DC supply. 3 lights are connected in parallel, and each draws a current. 3 lights connected in parallel. I'm going to model these lights as if they were resistors, because basically it's the same thing as far as I'm concerned. Oops, let's grab 1, 2, 3. And it says they're connected in parallel, so I'm going to draw them in parallel like this. There we go. And what else we got? 3 lights are connected in parallel. Each draws a current of 5 amps. So each of these is taking 5 amps. Now when you got like a set of parallel resistors or parallel components like that, the current is really being split between them. You can really think about this as terms of water. And if water was flowing in here, well, I can actually draw it on. It'd be flowing in and going down here and splitting. And I can draw the current on as like 3 separate jets or supplies of water. The 5 amps are being supplied to each one, and then they're collecting again at the end. So they're all coming together again. So there's 15 amps going in, 15 amps coming out, but those amps are being evenly distributed between those 5 lamps. Normally this is a lot more difficult because the lamps or the components are different sizes, so we have to sit down and calculate them all. But like this, we don't have to. They're just all exactly the same. Makes for quite an easy calculation. Alright, so each one has 5 amps on it. The lamps have a resistance of 3 ohms each, so we also know that this is 3 ohms on each of those lamps. Right, and then I guess I can use VIR. Oh no, we can use power dissipated over each lamp. Yeah, I'm jumping into Ohm's law, but I don't need it just yet. We need a power dissipated, so we need a formula for power. Power is PIV. And then we're also going to use Ohm's law, which is VIR, in order to get what we want, because we don't have the voltage of these. But of course we can find the voltage drop across each component by using Ohm's law. So this is the voltage drop is going to be equal to the I times by R. We've got the current as being 5, that's the I, and then the resistance is 3, so this will be 15 volts. This is the voltage drop across each component. So we can plug that in. We already know the ampage is 5, so the power is going to be 5 times by 15. It's meant to be a multiplication sign. Make it look more like 1. 5 times by 15. Grab my calculator, just in case I don't want to mess it up. And we can say 5 times by 15. And we get 75. So the power is 75. And because we talk about power, that must be in watts. Think about your light bulbs. They come in watts. All right. Cool. So that's the power dissipated by each lamp. Now the total power consumed by the circuit, if the total circuit is, the total resistance of the cables is 0.6 ohms. This looks like a lot more work. Part B. Because the total resistance of the cables, we did this one the other day. I had to think about it quite a lot. What does that mean? I mean, where's the cable? Does it mean all these cables? Are they in series or parallel or what? So I'm literally going to model this as being somehow this is connected to a power supply. So I'm going to model that as being my cables. I'm actually going to model my cables as being another type of resistor, a big fat resistor out here, big fat cable going around. And then this will be connected to a power supply, which I can't see or I don't really care about either. But just for the sake of completeness, it will look something a bit like this. This will be my cable. I can model that as my cable. Yeah, because if you're running something over like a kilometer or like 500 meters, then the cable has resistance. We do that later in another example, another question. So it will actually have a resistance of 0.6 ohms. That's great. Now, in order to do this, the total power consumed by the circuit, we have to, the total power consumed by the circuit. Well, I guess that these components are consuming 75 watts each. Oh yeah, we can do that. We can say these are each consuming 75 watts. So each bulb is consuming 75 watts, and this one's also 75 watts. Now I want to know, what is that cable consuming? Because it is consuming a little bit of power. It's like a heater. It'll be heating up your house or your ship or whatever it's running through. It'll be letting off heat. So we can use the same PIV calculation to work this out. I don't know the voltage. I do know the current and resistance though. Because I said earlier that all of these currents, these 5 amps, 5 amps, 5 amps, must be that the ampage is being split between them and then being collected together again. So I can actually say the ampage of this, the I, must be equal to 5, 5, and 5, so that's 15. And then so I got that, that's good. And then I need my resistance. My resistance is equal to 0.6 ohms. All I need is the resistance over the element, or over over the component. I don't need the whole resistance, the whole circuit. We're not doing that right now. So it's a really easy calculation. So let's put it all together. I'm going to say P is equal to IV. Of course, we can swap out the same way we did here. We can say V is equal to IR. So that's 15 times by 0.6. So the whole thing can be written as P is equal to, the I is 15, and we're going to multiply it by another one. So 15 times by 0.6. Great, grab my calculator. So 15 times by 0.6, and then times that by another 15. 135. 135 watts. That means 75 watts is being used up. Oh, each one. Wait a second. This is the power consumption over my cable. So my power consumption, my cable is gonna be 135 watts. And then we have to add up all of them in order to get the total power consumed by the whole circuit, right? So we can say total power is going to be 75 times by 3 plus the 135. Make it so you can still see it. 75 times by 3 plus the 135. 360 watts, my whole circuit. And 135 of that is in the cables. Great, now we've got to calculate supply voltage. Slightly different question. Let's write down here, let's go supply voltage. Right, so in order to supply voltage, how many points? Only 2 points. Yeah, it should be pretty easy then. In order to supply voltage, I need to know how much we're dropping over the whole circuit. Let's have a look. We can use, let's try VIR over each element. Do I really need to do it over each element? Maybe I can use PIV as well. Maybe I can use PIV. Oh, hey, I hadn't thought about that. I've got P is equal to IV. Well, would that be good enough to be able to get my V out of that? Because I got my power, my total power supplied. I could model this whole thing as being one component. So we could just say the whole circuit is one component and it's using 360 watts of power. The current through the whole circuit is 15. So I can work out my volts by transposing it. So let's try 360 divided by 15 is equal to V. Get my calculator. 360 divided by 15. 24 volts. Well, that sounds like a good number. Nothing too crazy. Sounds just right. Okay, on to the next question. Okay, question number 10. Let's have a look. A conductor with an effective length of this much and a diameter of that much and carrying a current of 25 amps at right angles to the magnetic field, the force in the conductor is this much. So we talk about flux density and magnetic flux. So I better get my formulas ready for this to start with. Flux density and magnetic flux. I know there's one that's FBI. FBIL sine theta. It's one of my magnetic formulas, and the other one will be, how does this go? Is it B is equal to, this is the magnetic flux, this is the flux density. Yeah, I think it's like this over the area. Now I gotta check which way around that is. Oh yeah, so we're saying this is flux density. I'm going to be saying that B is flux density. And how do you work out density is you normally take a mass and divide it by volume. So this time we're taking like the flux and we're dividing it by the area that it's acting upon. Okay, so it's a bit like density. It's not over a volume, but it's over an area. It's good enough. So this is my flux density, this is my flux. Flux density is the B. So this is measured in Tesla. And I can just pull out my components and put them all together. Let's see if we can do that. I'll zoom out a bit to fit it all on. Let's see. So we've got an effective length. So I think my length is equal to 300 millimeters. We have got to put this all into standard units. So that's going to be 0.3 meters. Diameter. Oh, I got to get my area. So my diameter, I don't need it right now. I'm going to put it over here in the other formula. My diameter is 9.5 millimeters. I'm going to be using that in a second. Let's scoot this off to the side so I've got a bit more space to work on. Okay. Then we are looking at a current. So the current, that's the I. I is current of 25 amps. That's fine. And then it's right angles. So the right angle means the angle that we're talking about here is 90. Sine of 90 is just equal to 1. So we can basically ignore this bit. And it's always like that on these exams. You can always just ignore the sign. All right. And then the force is 18. F is equal to 18. So it looks like I can just put it all together now. I got everything in meters, amps, degrees, and that's fine. All in my standard units. All right, so my force, let's do it over here. So the force is going to be 18 is equal to the B. Oh, I'm trying to find B. B is equal to X. I don't know what it is. I'll write it as an X. I is 25. And then my length is 0.3. And then sine of 90 just for completeness. All right, and then in order to solve this, we're going to transpose to get X as the subject. So I'm going to divide it by all of this stuff. So 0.3, and then like I said, sine of 90 is just equal to 1. So no need to write that on anymore. I calculated it in my head, really. I can check that. Sine of 90 is equal to 1. Multiplying 1 doesn't do anything. Anyway, let's do the rest of it. 18 divided by 25 times by 0.3. All right, I get 2.4. 2.4, and because we're talking about B, which is flux density, this is in Tesla. 2.4 Tesla. All right, that's the first part done. Now we move on to the second part, part B. See if I can scoot this across. That should be fine. Let's look at the second part then. We got our formula up here. And we need magnetic flux. I need to know my area. I've got my diameter. We're going to assume this thing is a cylinder. So let's look at or it's actually a loop. My bad. It's actually a loop. We're talking about something that looks like this. But let's not go there because this stuff is a bit strange. So we're looking at the area, and we know diameter, so I can get it into radius. Radius will be 9.5 divided by 2. 9.5 divided by 2. That's 4.75. So let's write that down. Even though it's in millimeters, it's 4.75 millimeters. And then I want to get it into meters. So let's divide it by 1,000 to pop it into meters. There we go. That'll do. That's 4.75 times by 10 to the negative 3, I think. Meters, yes. Okay, good. Area, therefore, is pi r squared. So let's take those numbers, plug them into pi r squared, and calculate it up. I'll just take my answer, I'll square it, and then I'll times it by pi. I get my answer, I'll get my area as 7.088 2184 times by 10 to the negative 5. That'll do. Let's just double check those numbers, make sure it's okay. 2184. Yeah, it's fine. Okay, this is my area. So I just need to pop this in here, and we're looking for the flux, the magnetic flux. So I can actually transpose this and multiply my flux density, which is this guy, with my area. So let's do that. Let's do flux is equal to flux density times my area. So that's going to be this number down here, the 2.4, multiplied by this number here, all of this. Grab it. All right. Okay, and we just multiply them together. So I get my same number on my calculator times by 2.4, and we get 1.7. So my flux is equal to 1.70117. And this is in Webers or Webers. is WEBR, which is a Weber. It's a Weber. That's it. We're done. On to the next one. Okay, so let's do question number 11. A plank of wood this big, that wide, that deep, floats horizontally in calm water. Take the density of the water to be this, the wood to be that. What's the maximum amount of mass it could support without it sinking? So we're going to be talking about a plank of wood that's in the water. Usually we don't do it like this. Normally it's sticking out of the water a little bit, but this thing is going to be loaded until it's just about at sinking point. Now the thing is, to provide maximum buoyancy, the plank actually has to be fully submerged. It has to be underwater. So the plank is going to be completely underwater. And then we're going to load it up with kilograms until it's at sinking point. And now the plank is either sinking and it goes all the way down to the bottom, or it's floating. Or it's just at equilibrium point. But that's a bit of a dodgy place to be, just at equilibrium point. We want to be on one side or the other. And there's one piece of information we're really going to be using about this, which is the mass of the displaced water, the water displaced, will be equal to, make this a little bit bigger, the mass of the amount this thing can support. Really, it's going to be the mass of the plank itself, and then we're going to add the mass of the load onto that as well. Okay, this is really the underlying physical principle of that, so I'll pop it up there. I'm going to write that to my examiner, so my examiner knows what I'm doing, what I'm basing this off, not just doing random calculations. So first of all, I've got to work out the volume of the plank. Let's write that down as a subtitle, volume of plank. It's quite easy. The volume is, it's given as, obviously the volume is the length times by the width times by the depth, but they give it all in different units, it looks like. They give me, my length is 4.88 meters. My width is 25.8 centimeters, which will be 0.258 meters by dividing by 100. And then my depth is equal to 175 millimeters. Divide that by 1,000. I think we're going to get 0.175 meters. Right. I suppose we can multiply all those together in order to get the actual, might as well write them out, to get the actual volume of this thing. 258 times by 175. Let's grab my calculator and type them in. 4.88 times by 0.258 times by 0.175. This is the volume of my plank in meters. 0.220332 meters cubed. And what we want is the amount of water that's going to displace. I might as well calculate the mass of the plank while I'm here, because I'm going to be supporting both the plank and a load. So let's get the mass of the plank as well. The mass of the plank is going to be its volume multiplied by its density. Volume multiplied by density. We've got the volume. The density is 710. It looks like I'm dividing this thing. I don't know. I want it to be a subtitle. Let's give it a bit more space. Right. Okay, so the volume is given as 0.220332. So we just calculate it. It's not given. And we multiply that by the density, which is 710. And that will give us the weight of this thing, the mass of this thing in kilograms. So I've already got the number in my calculator, actually. The 0.22, just times it by 710. And I get 156. So 156, 4357, 4357. And then 2 kilograms. That's how much this thing weighs, or it's this mass. All right. Now we're going to look at the mass of the water displaced. I think I can just keep scooting down. Let's have a look. Mass of water. Mass of the water displaced. Because this thing is completely submerged under water, it's going to displace a certain amount of water. And we have the mass of water up here as being 1010, as 1010 kilograms per meter cube. So with the same thing, same deal, we're going to take the same calculation. We're going to take the volume times it by density. And the volume of the water is the same as the volume of the plank, because it's the same thing basically. It's just displacing it. If you imagine a big hole in the water, well, this will be the same volume of the plank. So it's going to be 0.3322 times that by the density, which was 1010. Easy. Let's give that a go. So 0.220332 times by 1010. 53532 kg. Let's just double check that. This is how many kilograms of water I'm pushing out of the way, and we're only using 156 kilograms for the plank. So whatever we can add on to this to make them equal will be the load supported, because this question is asking us to calculate the maximum mass that could be supported on this plank without it sinking. So we're going to load the plank up with some kilograms. All right, so the load supported is going to be the mass of the water. This is the first thing we wrote up here. We wrote it way up here. The mass of the water displaced is equal to mass of the plank plus the load. So we're going to use exactly that. We're going to say the mass of the water is equal to the plank plus the load. Okay, so we got the mass of the water is 222 kg. We've got the plank, it's 156. So we just minus these off to find that plank. The load is unknown, but I'm just going to minus them off. So we can take I got the answer in my calculator already, 222.53532 minus 156.43572. 66. We're going to put down here, x is equal to 66.0996 kg. This is the load. The max load to be supported is equal to 66.0996 kg. Otherwise it's going to sink after that. Easy.